This example problem is in your notes, but we can't seem to get it done during class, so I'm going to do it for you in this video. This is a series circuit problem. So if I was going to draw this out, it could look like the battery here, and then 3 resistors all in the main loop with each other. So that a series circuit, remember, is a circuit that only has one path that charges can flow through. So for instance, if we're talking about conventional current would go from positive to negative around the loop here. And there's no second pathway it can take. So that's the definition of a series circuit. And in a series circuit, the way we calculate equivalent resistance is just by adding all the resistances up together. So that's the first step here. Equivalent just means total resistance. So we get to add them up, and notice these units are in kiloohms, and we don't like that. So we're going to change that to regular ohms. So you would just add up these 3,300 ohms plus 4,700 plus 3,900. And then you would get, when you do all that together, I'm pretty sure it's 11,900, but I just want to check. Yep. Okay, so that's a lot. That's okay. The next step often is to find the current. And in a series circuit, since there's only one path current can go, then the current through this resistor R1 here is going to be the same as R2 and the same as R3. So it's the same everywhere. And the way you solve that is through Ohm's law. So the current would be the voltage from the battery divided by the equivalent resistance, though. That's important. So the current is going to change based on how many resistors you have in here. So we got to use the total when we do series circuits. So we'd have 12 volts divided by this huge resistance. And when you do sig figs here, we're going to end up rounding it off to 0.0010 amps of current. Okay. Then it wants to know the voltage drop across each resistor. What we mean here is that we know the voltage is going to go up 12, like you get a boost of energy, right, from the battery. But then it's going to drop as it gets. So we know the potential energy of a positive test charge is going to drop as it gets closer and closer to the negative. And in this case, since there's 3 resistors, it's going to go down in like 3 steps, basically. So the way you solve for voltage drop in a series circuit is you do them each individually. You take the current, which is the same through everything, but that times the individual resistance value. So for this one, you get 0.0010 amps times that 3,300 ohms. And just because of the way the math works out, this isn't always true, but we get back to the number 3.3 volts when you do that out. Okay, so that means that between this spot and this spot, the voltage is going to drop 3.3 volts. Okay, and then I'll pick a different color here. Let's do R2. So if we do the same thing, and I end up with 4.7 volts, and then R3, the voltage will be, it'll drop the rest of the way down to 0, because by the time I get to here, right, that's kind of where I'm saying 0 volts is right there. That's the finish line. That's where a positive wants to be. So it has no potential left by that point. So then when you get that one, you could do it two ways, right? You could multiply again, 0.0010 multiplied by 3,900. Or you can just know that it all adds up to 12 volts. So it starts with 12, subtract 3.3, subtract 4.7 more, and you're going to end up with the 3.9. Okay, and then it says find the total voltage drop across the three resistors. Well, we kind of already talked about that, right? So um, you can write it out, or you can just say, oh, well, if from this side of the battery to that side of the battery, it's a 12-volt boost, then the rest of the way around, following the conventional current, we're going to drop down 12 volts again. So the answer is just 12 volts. But you could also solve for that by adding up the voltage drops. So you would have 3.3 volts from the first one, 4.7, and add on 3.9. Okay, that's an example of using the rules for a series circuit.